you. My name is Rafael Ferreira. I'm a professor slash lecturer at the Aeronautics Institute of Technology in Brazil. Today we are going to have a talk by Dr. Andy Gleadall from Loughborough University in the UK. And this is a webinar organized and promoted by the Aerospace Engineering Committee of the ABCM or ABCM in Portuguese, the Brazilian Society of Mechanical Sciences and Engineering, or Associação Brasileira de Ciências de Engenharia e Ciências Mecânicas. I'm chairing this seminar today on the behalf of the committee secretariat. So thank you very much for the opportunity, Dr. Daniel Souza. Our presenter is Dr. Andy Gleadall from Loughborough University. The presentation title will be Precise Geometry with Extrusion Additive Manufacturing, Toolpath Design, Computer Simulation, Experimental Characterization and Future Opportunities. A short bio from Dr. Andy. So Andy Gleadall obtained a PhD from the University of Leicester in 2014, studying mechanical properties of biomedical resorbable polymers during degradation inside the human body. After that, after his PhD, he became a researcher at the University of Nottingham, investigating hybrid manufacturing processes and additive manufacturing of tissue engineering scaffolds. And in 2017, he was awarded with a lectureship at Loughborough University, where he researches and teaches additive manufacturing. His recent research has focused on mechanical properties of parts produced by extrusion additive manufacturing. So he's gonna cover today some interesting topics on it, including full control G code, which is very interesting. Regarding to our interaction during this seminar, the presentation will have about 45 minutes. Then after that, we will have a questions and answers section with Dr. Andy. Your questions and comments you can post on YouTube, on the live chat on YouTube, either in Portuguese, tanto em português como em inglês. Andy will answer all the questions in English. So for us, and yeah, so thank you very much, Andy, for being with us today. It's a pleasure for us to have you here today and have your time. Thank you very much.
Great, thank you very much for inviting me and having me talk. So yeah, this presentation is going to be kind of capturing my research into a few different areas that are all related to precise geometry in extrusion additive manufacturing. So a bit about me. Yeah, in Leicester, it was my PhD. So that was really studying the polymers themselves, mechanical properties of polymers actually at the atomic scale. And that was for medical devices. The polymers that were used there, I actually then studied in Nottingham for additive manufacturing. And we were doing 3D printing of tissue engineering scaffolds, as Raphael said. And that was really required really detailed structures with tiny pores defining the everything, the mechanical properties, how the cells are interacting. And then in Loughborough, I was able to really do my own thing. So I moved a bit back towards mechanical properties. So I've put my kind of general design interests here on the bottom left, my general research interests, and combined those various aspects from what I'd done in my PhD and undergraduate and my research career. And I've really focused on mechanical properties and how to design toolpaths that really get good mechanical properties. So that's kind of the focus of today. And then a little bit about me. Barbecues are my favorite thing in the world for sure. And you can see on the right here, this one is actually one I made myself with some wood from the little forest behind me. So I really like engineering in general. I've always just been a kind of making stuff has been my hobby. And then for sure, American football, which is quite unusual in the UK. But I played that and coached that. And hopefully we'll do some research in headgear or something for that at some point. So this talk, it's toolpath design, computer simulation, and experimental characterization. So I'm going to go through it in that order in the next few slides, all related to precise geometry, and then briefly about kind of where I see things going in the future for me as well as kind of in general. So a brief background, extrusion 3D printing, the most common way, we basically have a reel of polymer filament that is fed into the back of a hot melt chamber that then melts it, and it's extruded out the tip of a nozzle, and then that nozzle is moving around and 3D printing whatever device. So this was a tissue engineering scaffold for a nose. And the general step to get to that tool path for printing the nose, the general steps, is typically you have a 3D model, which will be whatever, your tensile testing coupons in many cases, or your anatomical models, and they're going to be STL files. You'll take that into additive manufacturing software and slice it into lots of layers, and then you'll look at each layer individually and decide how to do a print path for that layer, and then put them all together as a big continuous print path that is then sent to printer for additive manufacturing. Of course, then you'll characterize it or evaluate it in whichever way you want, and often come back and revise either your 3D model or your toolpath generation strategy. Then quite a bit of what I'm going to talk about today is a different approach for that. Rather than that idea of CAD model, switching to an STL file and then layers and print path for each layer. It's designing the print procedure right from the beginning. So you don't actually have a CAD model at all. You just think, where do you want the actual nozzle to move around, in what order, and what do you want it to do while it's moving around, whether it's extruding material, how fast it is, or not extruding, and so forth. So it cuts out a lot of steps, which really enables some things that are just either impossible normally or would be really, really difficult. So they all sort of started in this direction when as I started that printing those tissue engineering scaffolds, and I knew what print path I wanted to print with a printer, but it just wasn't possible for me to get that. So I was just kind of confused as to why I wasn't able to tell the printer what I wanted it to do. And that's when I started writing G-code, which I'll get onto in a bit, about how to control the printer. But secondly, once I then got the printer doing what I wanted, what was actually being printed wasn't necessarily what I was expecting based on the toolpath preview. And I could see there was kind of blobs of polymer in some places, gaps at other places. And I could see that generally these were what you'd expect if you just thought about it a bit. And I thought that looking at them, basically, if I just took these 2 points into consideration, that gave me most of the information I needed to actually get a really good prediction of what this potentially quite messy structure would be. And it is literally, as the nozzle's moving around, that's where the material's coming from. And very simply, if you've already got material there, you can't put more. So it's got to spread out and occupy the sort of nearest space that it can. And those 2 points really led to the first simulation method that I'm going to talk about, which was to predict the microscale geometry. So in terms of simulation, it means lots of different things. Here I'm talking about simulating the deposition of material to get a prediction of the 3D structure. Then I can use that 3D structure as shown on the right for things like mechanical properties, finite element analysis. But it's the most important thing here is getting this prediction of the actual 3D model. And then you can use it for lots of different things. And so that's what Volco does, and volume conservation is what it's short for. And that's what I was just talking about with that nozzle moving around. And I'm going to go into kind of a fair bit of detail about this, and hopefully from the basics of it through to quite a high level of detail, and then talk about some of the kind of uses of it a bit more broadly, because obviously there's not enough time to go through everything in full detail. So the key thing that Volco was doing was, typically you'd expect the extruded material to have a constant cross-sectional area. As you print a line, the previews you get in additive manufacturing software and things would expect it to be like these left-hand two images. But I could see in my printer parts, it wasn't. It was varying in lots of different ways. And this shows you a couple of examples. So the print path on the picture on the left is a kind of top-down view of this scaffold structure on the left. That's what's expected. That's what we were sort of trying to achieve. But when we actually print it, you can see you get material deposited where you didn't really want it. You get variation in filament width as it's crossing over existing deposition and things like this. And these are significantly affecting mechanical properties and porosity and so forth. So then that's where I came to this idea that basically simulating the material coming out of the nozzle, and this is showing an animation of that. So this is lots of tiny little steps. Each step is depositing a certain amount of material according to a kind of nearest distance criteria. So that naturally forms a spherical shape. And you can see at the bottom left, showing an animation of it being done at a much larger, well, a much more large structure, but the same scale as what's shown here. So that's to simulate this kind of lattice structure. I was doing it for tissue engineering, but this kind of geometry is often used inside parts, for porous parts, can be for filters and all sorts. So we have this kind of breaking it down from a continuous process into lots of short steps. So as the nozzles, we're just thinking about it like step, step, step. And that each step is what we're simulating in Volco. And it's basically saying how much material is deposited for each step and how far along our toolpath are we moving with each step. So then we have our point where we know we're depositing material, and we can have a very simple criteria of just looking for whichever voxels in this 3D environment that I create full of voxels which contain either air or material. And basically it will just search with a gradually increasing spherical kind of region and just put material in until we've got enough material as we expect from the how much we've told the printer to extrude. This is showing then the actual voxelated model, and clearly if you choose tiny voxels then you'll get much higher resolution for your discretized structure. So then using that, what I did in the publication was go through this workflow. We have our machine G code that we're sending to our printer, telling it where to move to and how much polymer to extrude. We use that to set up the simulation to generate the 3D structure. Out of the simulation, we then produce this STL file, which is then imported into finite element software. This was Abacus, and used to run simulations to then predict what the mechanical properties would be. So one key thing that is always very important is the amount that the polymer is kind of squishing as you deposit it. And this is a good way to test whether the simulation was working. So you normally print layer by layer, filament on top of another filament on top of another filament. That's all fine. If you do the same again, but everything's the same except you don't leave as much space in between the layers, then you've got this interference between them. We know we need conservation of volume, so then the filaments will actually expand and become wider just because there's not enough room for them to take this tall cylindrical shape. So this was what we did in a quick validation using 3 different spacings for each layer. And then on the top here, this is experimental micrographs of the structure shown on the left. And then at the bottom, that's the Volco prediction. So very simply just showing that this kind of works. And then using it for more intricate structures at the crossing over points, you can see on this how the filament is getting wide, then narrow. And that's what we were able to predict with this very, very simple idea of just dumping material as close as possible to where the nozzle currently is, based on how much material. So quite an intricate structural prediction for such a simple thing. Using that model in finite element analysis to get the predictions of mechanical properties, I was predicting compressive modulus for these specimens. So we could do the experiments and then compare. And on the right here, I'm showing this kind of value of this approach, where the green line is the Volco models geometry being used, and compared to the experimental data points, it's obviously matching the trend very well as we changed a parameter in this structure, which is actually layer thickness. So as it goes smaller, the structure is getting more and more dense, which is what this image is showing here with the top FEA image is showing it when there's quite a lot of space between the layers, and the bottom one is when it's got very little space between the layers. It's not smaller. The bottom one's not smaller because I've compressed it more in FEA. That's the actual printed structure. But on the very bottom left, you can see the actual typical way you would predict, potentially get a prediction of mechanical properties, which would be to produce a CAD model based on the toolpath using, say, an assumption of cylindrical or oval filaments or something. And with that model, that exact geometry that you see on screen here compared to the Volco, when we did finite element analysis on that structure, that's what the red dotted line is in the plot to the bottom right. And you can see it just can't capture that trend because it's not capturing the fact that the filament is getting wider at crossover points. So this approach is not really representing what's going on really in the printing process. So that was the original Volco, and then actually how I met Raphael was talking about or doing some collaborative research to extend it to different types of structures. So a really common structure is lots of filaments aligned side by side, and in that case, it made sense to change the strategy for Volco. So his student, Raphael as well, developed a new algorithm for the deposition, which wasn't just spherical. And this was an algorithm that was optimized for filaments being deposited side by side, where this strange thing happens that as you, in this structure on the bottom right, this is the experimental image, you can see the filaments have this quite odd shape, and it's because it's printed from left to right. So when it prints the next filament along, it's easy for the polymer to go on top of the filament, but not so easy for it to be squashed underneath. So you end up with these triangle-shaped pores, and that's what his deposition strategy factored in. So it analyzed at what point it was making contact with the previous filament and how then at that point the deposition would change. So it was still very simple, but it could get these predictions for a different type of structure. And I think there'd be lots of other versions that could be done for different types of structures and then potentially all brought together. And you can see the prediction of the microstructure is really nice. Even the asymmetry of these triangles is remarkably well predicted by the Volco model on the left compared to the experimental one on the right. Then another extension of it, or not an extension, a kind of use of it, was to compare to a better approach at CAD modeling. So the one I'd shown before was what was state of the art at that time. Then 3 years later, someone had developed an alternative way to generate CAD models for based on the toolpath, and then they did a nice comparison to the CAD model there. And it was Volco was better sometimes, the CAD model was better at other times, but it was just an interesting study to show that there is this point that needs to be considered, is how well you're able to get a prediction of your expected geometry based on the toolpath. So then a final example of it being used, this is for drug release structures. So we printed some tablets. This is just showing a rectangular specimen, but these were also printed in tablet form. And the drug was released from these structures, and we used Volco to simulate the actual 3D geometry and then get a prediction for the surface area and the porosity and how drugs would be released from these structures. And the great thing with Volco is it's just so simple and versatile for all different toolpaths. So this was a slightly unusual print path that you saw there to get different properties on the inside and outside sections. And it's just a case of sticking in different G-code to get the different predictions of the structures. So then this is the last point about the simulations, is integrating these kind of capabilities into print path design is where I really want to go next. So rather than the current approach would be, say, to give me 50% infill, it would be defining what properties you want, because nobody really cares about infill. You might care about pore size or porosity or properties. Infill percent, which is the kind of nominal porosity of lattice-like structures inside 3D printed parts that you can set in additive manufacturing software. When you choose a percentage for that, it's just a kind of indication of what sort of density you want, whereas you're generally doing that to achieve something that is more specific. So this is the kind of things that I'd want to allow people to say. So it could be in the medical device, it could be surgeons saying that they need a certain, and actually far beyond, anyone just that isn't an expert of additive manufacturing being able to just say, I want this Young's modulus or this strength, and being able to do that. Or an example here, very specific about the pore sizes and so forth. So that's what I'd see going forwards, the ability to actually simulate the mechanical properties of little building blocks in really good detail, and then put them together to get an actual true prediction of your final part. So now moving on to actually designing print paths for precise structures. Just back to the G-code stuff. So G-code is basically what we're designing in this case. You don't always need to use G-code. Different systems will have different languages, but basically it's just a list of instructions that are telling the printer what to do. So this is a proper example of G-code. And the first bit is saying that I want the printer to move. The next bit is saying where you want it to move to, and the speed, and how many millimeters cubed of material you want it to actually extrude while it's doing that. And there'll be lots of different formats of this, but this is one that is true for our printers. So this is just written in a big text file and sent to the printer. So you can write this by hand to do relatively simple things, but it gets a bit painful to do that for more complicated ones. And the sort of things we might say for this type of structure, we had this issue of blocked pores at the top, where it was critical that we didn't have blocked pores because we were growing cells in here. The G-code for these 5 lines is very simple. We just need to go to a certain Y value, a certain X, certain Y, certain X, and so forth. And it was the fact that we had that G-code was causing the problem. It wasn't the printer's fault. It was the print path. Then a very simple adjustment to it, just to tell the printer to move a little bit outside of the area before moving across, and then go up to the side and move a little bit outside before going across. That was all that was needed to shift these defects, which are kind of unavoidable defects for this system with this very flexible material. We couldn't accurately control the flow in such a way to just print it perfectly. So we shifted the defects from inside the pores to outside the structures, where it made no difference at all for what we were researching. And that's the kind of thing. It's very, very simple, but it can make a massive difference to actually the quality of the research being conducted. And we took that then to actually design a structure where we wanted porosity in the side walls, which are quite difficult to get porosity. And instead of using the conventional approach of going to the wall, turning 90 degrees and then turning 90 degrees and coming back, we came back at an angle of 45 degrees, which cleared out all this space. And again, it's just a tiny, tiny change, but the actual side wall surface is incomparable between those two, because it's just thinking about what we want and what toolpath is actually good for what we're intending to get. So that's the things that come when you can design the print path exactly how you want. I could change this angle to be whatever we wanted, and that just doesn't exist in off-the-shelf software, because no one else needs this exact thing. So they'll have the things that the majority of people need, but for a very specific application, they won't have the perfect combination of options for you. So that work was collaborative, and I created an Excel tool for the research that I was working with to actually produce these sets of scaffolds parametrically. They could adjust the porosity and various things, and then generate the G-code, and off they went. So that was the first time I started kind of putting together a G-code generator, and this was probably 2014 or 15. And it worked really well that I could put my effort in, and then the actual person that was printing and doing cell characterization could do what they were good at, and neither of us be kind of held up by the other one. And then what led me to take that forwards to actually full control G-code designer was when I became a lecturer at Loughborough, and I started running student projects. And this is a nice example of one, where it made me realize it would just be hugely advantageous if the students were able to produce their own G-code without having to go through all the steps that I went through as a researcher to write scripts to do that and everything. So here, the student was just creating some demo specimens to test the capabilities of a printer printing at the smallest scale. And this one at the top left is for printing hollow cylinders. And depending on the wall thickness, if it was wall thickness was set to exactly the same size as the nozzle, we got this nice round circle. If it was set a bit wider, we got this real weird mess. And looking at the toolpath, it looked like this. It was printing a circle, and then because it was supposed to have printed 0.6 millimeters wide, and the first circle was only 0.4, it's then thought, I've still got to put in 50% more material. So it just kind of dumps it in these reasonably symmetrical manner. And that's just because the algorithm set up for that slicer is not designed for this kind of scale. So the slicing algorithms can do amazing things when you're working within what they're good at. But here, it was just making an illogical decision about how to do that. With custom G-code, we can print exactly the same circle and obviously just set it to extrude 50% more material, and we'll get the actual width that we want. So that structure, that project, I wasn't intending to do custom G-code, but it became clear very quickly that the most important thing here was the toolpath and how the toolpath was being generated, and that was dominating everything else. It wasn't about material properties or printer capabilities. It was just about whether the toolpath was suitable or not. So then I realized that the students being able to produce their own G-code would be really useful. And that's when I started producing full control, where they could describe what they wanted the printer to do in terms of things that are a bit like CAD, saying I want it to print a line or a circle or polygon. And if it's printed 5 lines, you might then say, now do a polar array of them as you would in CAD, and print them in 6 more different positions on the print bed. And maybe for each one, change something about it, print it a bit wider or something. So it was this kind of a feature-based design process almost, where they could describe what they wanted without having to actually code, without even needing to understand G-code actually, because they're just describing the sort of movement of the printer, not the G-code commands. It's then full control that takes it and produces a G-code. So this is an example of one of the first student projects I did where we used full control. And the structure at the bottom right is the kind of lattice that we were trying to print. And this shows the kind of the workflow of designing that toolpath. So starting at the top left, we knew this was our unit cell that we wanted, but it was obvious printing one unit cell and then the next one and then the next one wasn't a logical print path. It was better to do one layer going all the way up and all the way down, all the way up and all the way down, and then the next layer doing all the horizontal ones. Because that would be the nice, neat way to print this structure without the nozzle always changing direction and jumping around and having to stop and start extrusion and everything. So once we've got this concept, we then need to do the technical details about exactly how to describe the position of the nozzle. So it's pretty simple, really, just finding the coordinates of the center of an arc and then how much, what angles the arc is going to. And then that can be put into full control. So the student's able to write that they want an arc with a certain center, certain radius, going from minus 45 degrees, sweeping round by 90 degrees to get to the new point. And then another arc coming back round here. So that's what's shown down at the bottom. And then just repeating it or reflecting it, then repeating it again, and then repeating it with rotation. So building up from very simple details at the top right really into this toolpath, which is just the quality that you'd get from printing with this is incomparable to what you could get from creating a normal 3D model and putting it into a slicer. We've tried that as well. So that was how full control works, and it was published as open source, all just built in Excel. So as long as you've got Excel, you just download it, and then everything's written in Visual Basic behind it. And what it also offered the opportunity for was to define toolpaths in terms of mathematical equations. So this spiral, the equation for that is very simple, just cos t sine t for x and y, and then t is going from 0 to 1, and z is just constantly increasing. So these are the actual plots of that as t is, or in this case, t is going from minus 2 pi to plus 2 pi. So in full control, you can write this form and then say, I want a toolpath to go with these x, y, z equations as a function of t, which is a common way to write parametric equations. And then you can produce structures like this with a really simple parametrically adjustable equations. So then from that, we moved on to gyroid-like structures, and these become really, you're able to then skew these and change their geometries really nicely because it's parametric design, which is quite different from infill in a normal additive manufacturing context, where you typically figure out an area and then kind of overlay a grid pattern onto it or something, and then just cut it out. And if you've got half unit cells, then they'd just be cut out, and you kind of print half of them, which leads to some sort of not the neatest structures necessarily. This was some research then taking it forwards towards the print path is often thought of in terms of X, Y, Z positions, but actually the extrusion width is a really critical aspect that you can control really neatly. So these 4 lattices at the top right all have exactly the same square wave print path. The only thing that's changing is the amount of deposition as the nozzle is moving from bottom to top or left to right. So in the one on the left, the nozzle is printing more on the left, less on the right, and more at the top and less at the bottom. And you can either achieve that if the material is quite responsive by just telling it to extrude more or less material, or if it's not a very responsive material, so some hydrogels and things won't be, or concrete and things, you wouldn't want to change the flow rate. But you can then change the nozzle speed so that if it's spending less time somewhere, it will deposit less material. And that's what we did here. And the one on the right, you can see this really graded, nice structure where it's purely because we've varied the extrusion width. And taking that towards the mechanical properties research, then with our dog bone testing, we were noticing that there were defects at the transition from wide section to narrow. And here you can see the defects are kind of shoulder junctions. Often you'd have a perimeter printed, and then these steps would actually be internal, and they'd lead to these stress concentrations and pores, which lead to failure, not in the gauge section, but in the transition from the wide to narrow sections. And that then ruins your test, because you're testing the strength of the defects in a part rather than the actual material. Whereas on the right, with this idea of constantly varying the extrusion width, we can go from wide to narrow in terms of the overall geometry and the individual filaments to get really good continuous deposition and good quality. And that has enabled us to do loads and loads of mechanical research, which I'll talk about a bit later in this talk. During COVID, one of the things we were working on was these printed masks, which I know a lot of people were. From our point of view, it was slightly different because we were working with Toyota, who had a very specific requirement for their mask in terms of materials, printers, and geometry. So we couldn't really optimize the actual design to be optimized for additive manufacturing or choose the best material for additive manufacturing. We had to work with quite challenging constraints. But using full control, it was one of the first times I used it for printing something that's proper. We printed 2000s of these masks in total, so stacking them at the top left was really critical for productivity. But you can see the kind of comparison between the toolpaths. The default one that you get from a slicing software has the multiple passes around the perimeter, and then the kind of strange zigzag infill, lots of little travel lines as the nozzle is moving between the kind of the front and back sections. And this was a nightmare for the workers at Toyota to actually clean up. They were having to scrape out lots of bits from inside the gap where the actual visor was going, and it was taking them maybe 10 to 30 minutes per mask to actually clean them up sometimes. But then with full control, we knew what the limitations of the material were in the printer. We knew there were going to be defects. We couldn't just instantly stop printing and start printing somewhere else. It was going to leave a string because we were printing so fast, but we were able to control exactly where all those defects happened. So there were these holes in the mask that you can see on the front and sides, and they were a really easy place to put the defects, because then we could come with a drill and just drill through them, get rid of the defects, and it took 10 seconds to post-process the mask instead of 10 minutes. And that kind of awareness, really designing for manufacturing and post-processing and function, were all coming into this, and it was a really nice opportunity to really test out the kind of concept of truly design a print path rather than designing the geometry and then figuring out a print path afterwards. So then for some more unusual things, the stuff I've talked about so far is mostly normal type structures, but when you're also designing the print path, you can do completely different types of geometries. So here, this is printing strings, and you'll see just moving the nozzle around really quickly and depositing these strings, and these strings become down to 1/10 of the nozzle diameter. They're obviously highly aligned polymer chains and everything, so the mechanical properties will be completely different. In this case, we were also printing with drugs, and the drug release rate was just vastly different depending on the string diameter, because the surface area to volume ratio was just hugely different. So this is the drug release, this plot. So as time is progressing, we're getting more and more drug release, up to typically 80%, and the big diameter filaments were taking 400 minutes maybe, whereas the strings, it was much less than 1 minute. So here we could now print with the same material and the same printer, but get completely different performance just by tweaking the what we're actually printing, which is great for drugs because we don't really want to have to print lots of different materials. If we can get lots of different treatments by printing the same material with the same process in slightly different ways, that's a real advantage. So then on to experimental characterization. The focus of this is really on mechanical properties, but for sure this could translate to other things, and particularly what my group has really focused on is the mechanical properties of the interface between 3D printed layers. So this is the the most common thing that people would say is one of the weaknesses or the challenges of extrusion additive manufacturing, is the fact that you have the layer lines and you've got that interlayer bond, and it's weak. The material is weaker when you test it in the Z direction, normal to the plane of the layers, weak compared to its strength when you test it in the plane of the actual extruded filaments. So I had a student project look at this when I was first here at Loughborough, and printed the ASTM specimens using standard slicing software. And when you fracture them, you get a really nice, clear view of the actual kind of bonded area. So this pink outline is showing what the actual bonded area was of this line here. There's this diagonal line as well. That's when the nozzle actually moved from the end of one layer to the beginning of the next. It's not supposed to print. It's not part of the design. It's just something that had to happen between layers. But clearly it's significantly affected the actual interlayer bond. And this area here is just really odd and hard to, you could never be able to predict that it would look like this. And it's not what you want. You're actually expecting this kind of green area is the area of material. And ideally that would all be perfectly contacted between the layers. Clearly it's not, but the difference between the kind of thin contact area on the last filament, then wider, then wider, then wider, it's really a strange thing that's going on. And your mechanical properties are therefore dominated by really quite unusual and probably not factors that would be repeated for a slightly different print path. So we realized that if we really wanted to get good fundamental understanding, we needed to switch to something where we'd have really good control and be able to evaluate the mechanical properties and the contact area and everything. So we switched to a single filament stacked on top of a single filament and single filament, so that we'd have a wall that was just one filament wide. And that's what we've got printing here. So we achieved the dog bone specimen by controlling the width, as I showed in some of the earlier bits. And it seems really simple and logical now, but I remember as we were developing this, first we were thinking we can go from 2 filaments to 1 and all this. It was at one point we just suddenly realized, oh, we could transition from wide to narrow, and that would be even better. So, and it worked really well. We can print these boxes really quickly, get lots of testing specimens by cutting nice rectangular specimens out of the box, which is really advantageous over cutting a dog bone, because we don't need complex dies. When you do have a complicated dog bone die, it's quite difficult to get the actual specimen out of it without damaging it and various other things. And this was a really great specimen for then fracturing it and getting really good understanding of what the interface was like. You know, here we have a really consistent bond along the length of the filament compared to over here, where it's really dominated by the nozzle changing direction and stuff. It also allows us to do nice finite element analysis to support our experimental understandings. That's what we're seeing on the right, how the experimental results, which are the bars, really fit in nicely with what we'd expect from the simulation data. Whereas again, doing a finite element analysis of this contact area would not really be a sensible thing if it's not repeatable. So we did our testing, and we were quite aware of these grooves in the side potentially having stress concentrating effects. And these are the results for testing along the direction of filaments. So this is when we're printing in the X direction or Y direction and making the filament get narrower and wider by changing the extrusion rate. So when we're testing this, it's really continuous polymer that we're testing. This should be like bulk strength polymer, and it is from our tests. In the one on the right, it's now layer by layer by layer with lots of interfaces between the layers, lots of these grooves, and we're testing the force. And clearly, the one on the left sustains a higher force, and that's normally what we'd see and say the interlayer bond is causing an issue. But actually, when we looked at it, which we were really able to do easily because it's such a simple specimen, and measure the width, then the width being 25% narrower, it's kind of like gouging out a groove in something. And this one I could snap really easy. This one I couldn't snap easily at all. And that's basically what we're doing. We'd expect the force to be less, and it actually is. On the previous slide, it wasn't far off what you'd expect the force to be, just based on the cross-sectional area. On that slide, we're plotting force versus a displacement. When we plot stress versus strain, it's still not that obvious, because it's not clear exactly what area you should use to calculate stress. Of course, for us, if we're calculating strength, then we want to calculate the area of the narrowest bit. But that's quite a challenge to do on a geometry like this. So by simplifying it and really analyzing the micro scale geometry, we could find that actually it doesn't seem like the interlayer properties are any worse than the bulk polymer. And we tested this theory by taking one of the specimens that was solid, that was printed and tested along the direction of printing, and we manually scored it with a little blade to create a groove that was the same size as the grooves in between the layers. And once we did that, the force they got, it was exactly the same in this case. I'm not saying it's exactly the same every time, but it's within experimental error. The properties of the solid polymer just matched that of the polymer that was tested in the Z direction or between the interlayers. So it's suggesting that actually the bond is perfect, and it's just the geometry that needs to be considered. Now we back this up with really detailed analysis of the fracture surface, which is again only really possible because we've taken it from this large complex toolpath for tensile testing specimens to these very simple ones. And also with the size of these, they're very quick to print, means we can do lots and lots of different tests and get really good broad understanding. So these are all different structures that were printed with exactly the same nozzle and material and printers, and we could then calculate the bond strength for all of these to get a really good understanding of whether the findings do translate beyond our immediate study design. So that's an introduction to some of the mechanical testing that we've done. I've spent the last kind of 4 years focusing on this, so that we've got a lot of publications on that topic and nowhere near enough time here to go through them all. But if you are interested, then check me out on Google Scholar. And I've just picked a couple of examples which are quite interesting to show specific things that we've taken this to investigate. So the one on the left was when we were finding this thing that potentially bond strength was actually really good, or the same as the bulk material. And I'm not saying this is for all materials or anything like that. It's just that unless you measure the bond area and check, you don't know. So we did, and now we're testing, does this translate to different conditions? So here we printed the same material, same printer and everything, with temperature ranging from 180 to 240, with speed ranging from 250 to 4,000. This is a 16-fold increase, and with layer time changing from 5 to 40 seconds. So that's an 8-fold increase in layer time. So clearly hugely different thermal conditions, cooling and everything going on here. But the results of that study were basically finding that the bond wasn't affected. And that really gave us confidence that the interlayer bond was actually molecularly very sound. And it's just considering the geometry is really important if you want to evaluate the mechanical properties. Then on the right, this is my student that followed on from the one on the left and was really interested in carbon fiber and fiber reinforced polymers. So here, again, because we've got these quick and easy to analyze specimens, they were able to do loads and loads of tests. So here I'm showing 4 different materials with and without carbon fiber in 2 different directions, the principal like worst and best directions, directly along the filaments and directly normal to them in the Z direction. So these are 4 results. It's also tested these for all different temperatures and all different extrusion widths and layer heights and all sorts, to get an understanding of really what's going on with fiber reinforced polymers, and has found lots of interesting trends that apply across all different materials, ranging from extremely flexible ones that might have, or ductile ones that might fail at 800% strain, down to ones that fail at 10% strain or something. There's also found trends that are different between those materials, obviously, but it's kind of a huge, beautiful load of data that's really good quality and can understand then what's going on at the simplest scale, which can then really inform how you design and evaluate structures that are more complicated, lattice structures or brackets and things for aerospace. Would be using this understanding to know what you actually should be designing. So then finally, kind of where I see things going Next, got 4 videos in the next slides that are the next slides, which describe these first few points. So pre-validated print paths. The idea being you designed a print path. Now, if you change the geometry, it's still the same print path. It's just a bit bigger or a bit smaller or a bit elongated in one direction. But because you're not changing the print path, say, from 2 unit cells to 3 unit cells, or worse, it would often be, say, a partial 1 unit cell to 1.5 or something if you increase the size of your object and the internal infill was not an equal integer division of that. Then this really is great because you can design a print path and know that it's going to work even if you change all the geometries, which is just not the case normally. True freeform 3D printing is where rather than just printing layer by layer, you can actually print vertically and angles and all sorts. Expansive characterization, this is where instead of testing maybe 5 settings, you might test hundreds or thousands, and then combining with AI and in-process inspection, in literally a few minutes, you might have tested thousands of parameters and got really good understanding of their interactions and everything, which is just dramatically different from the current calibration procedures that you'd see on typical 3D printing part websites. And then finally, rethinking optimization and how design for additive manufacturing might work if you really truly design for the capabilities of the system. Secondly, in situ inspection, which I think kind of ties in with multi-axis and multi-process manufacturing. There's adding axes and things makes it really challenging to generate tool paths with the conventional methods. But actually, when you're designing a print path from scratch, it doesn't really make it any more complicated if you're designing a 4th axis on top of 3. It's a little more complicated, but like not much more. So when you're really designing those print paths and thinking about what the axes are doing, a rotational axis or 2 rotational axes are just a kind of natural thing to design. So I think stepping back from the current conventional workflow will really enable impressive, really valuable multi-axis manufacturing that isn't complicated. The full control version I've shown you so far has been in the Excel user interface, but over the last year, a guy from the US called Dirk Leers has been guiding me through rewriting it, rethinking it from the ground up in a much more versatile way, with predominantly based in Python, but not fully. And now this is enabling far, far different things than what we were previously doing. So integrating the external data, for sure, the multi-axis stuff is coming. So from a personal point of view, that's going to progress. And the website, a couple of the models I'm showing you next are on, is one of the outputs of that so far. The educational prints is something I think is really an opportunity there to actually print test pieces that really highlight the process capabilities, not test prints that highlight slicer or additive manufacturing software capabilities. So this would be things like increasing flow rate until the printer can no longer print any faster, and then seeing what that looks like. So it's not a toolpath thing, it's a printer hardware and materials capabilities thing. So educational prints that can really, from somebody going and using a printer for the first time to within a couple of hours of that, having a really good understanding of all the key challenges that you have when you do additive manufacturing. And finally, an open source 5-axis system is, we've developed this, we're using it, and we just need to pull our fingers out and release it, but that's going to be released imminently, basically. So these videos here, this is showing the pre-validated print path. So here, this lattice structure is fully parametric in loads of different ways, and now it can work if somebody puts in their own phone dimensions. they can get a new print path just for them, but it's basically identical, and I know it's going to work. It's because I've tested it with lots of different geometries, and it works. So this is a kind of the print path sequence and everything is designed, but then how pointy these waves are, how many of them there are and stuff, that's all entirely variable without making the print path any more challenging to print or likely to fail or anything like that. And I will just show this video. This is one I released today, and this model is available to download just from this afternoon. And this kind of truly designing these lines, these are actually printed double the width of the nozzle diameter, and they are the height, the layer height is the same as the nozzle diameter. Whereas in default slicing parameters in Cura, these lines would be printed with 3 lines, and it wouldn't be a smooth continuous print path unless you just wouldn't get that. So here it makes it really simple for it to print really quickly and smoothly. And this is showing the kind of how it goes around that print path. And it does the whole thing without any travel at all. So it will print this whole layer and the whole part, all the layers, without ever having to stop the extrusion and move the nozzle while it's not extruding. It's just one continuous smooth path. And the way it works on the website is just demoed here, where someone can come in and put their unique details and update the design and get out basically the same tool path. This is changing the number of fins, the number of angles. So that's the kind of thing I'd see. Obviously, this is a kind of not critically important part, but this type of toolpath could easily be used for something that is a supercritical component, and being able to adjust it in that way to change its density or change how wide the filaments are at different points would enable optimization in a way that just wouldn't be possible with if you haven't pre-validated the toolpath. This is the calibration. So here we're printing 500 unique combinations of retraction. Retraction is when the printer stops printing, it does something like pull the material back up a little bit and then moves really quickly. That is what this is doing with 500 unique combinations in this single print. And then on this design, you can then investigate 4 different factors. So in 4 prints with a total of 15 minutes printing time, you've got 2,000 unique combinations of printing settings, which can be used to really evaluate what effect they're having. And this is showing, so as we move from left to right, slightly adjusted one print setting. As we move from this line printing that way, it's tweaking something else. And there's this bunch of 4, that's tweaking something else, and so forth. And this also ties in with the educational point. So here, no one's ever going to retract at this speed, but it really highlights what retraction speed does, which is how fast you pull the material back into the nozzle, because it has a completely different defect associated with it than retraction distance. It looks nothing like the same defect. So what this is kind of from an educational point of view, you can see what different parameters lead to in terms of the type of defect, and then that would really help with evaluating when you get really subtle defects, what the underlying cause of them might be. So that's the picture of the 4 of them. This is 3D, true freeform 3D printing, where we're printing vertically. And this was the result of 2 student projects, primarily from Toby Lung and Danny Sprague, where they gradually got better and better capabilities at this, until by the end of the second project, we could create this really vast range of different structures with vertical lines, horizontal lines. And this is printed on your cheapest 3D printer you can buy, with just non-optimized material. We didn't optimize temperature or anything. This was all just controlling speed and So that's the different structures that he was able to print. And just, yeah, by optimizing speed, and he machined a slightly pointier nozzle than normal. And then this is about the kind of rethinking what's possible. So this overhang is just printed in the middle of the air, and it's because the print path is so neat and consistent that when the polymer comes out of the nozzle, it really just wants to stay where it is. It's contacting some material to the side. Gravity is very small in terms of its force on the printer compared to its stickiness to the neighboring filaments. So printing these kind of things then, and we've done this with various different geometries as well, obviously stacking on the top here, so with corners, printing inside instead of outside, and it just works really well. And the beautiful thing here, this has kind of been all over social media with people printing these and putting cool music on them and stuff. And a number of times people have just written, I went to the website, downloaded it and printed, and it worked perfectly first time. It's just been really great to see, because this is, in theory, this is kind of really risky printing. It's really difficult. We're printing stupid stuff floating in the air. You wouldn't expect it to work on all different systems with all different materials. But apparently the simplicity of the print path and the kind of it's the lack of any forces really trying to make it break is more important than those kind of subtle differences between people's printers. So then it's not a quirky kind of one-off demo. This could really happen in a part, but the design constraint here is it's going to be much easier to print if you have a similar kind of overhang on this side than on this side. So one of your design rules now might be to make your overhangs generally as symmetrical as possible, or as similar on both sides. And that is not a current design rule. That rule won't be written anywhere for any additive manufacturing design rules, because it's not required for current slices. But if you wanted to print like this, that is a new design rule that would be good to make it as printable as possible. So that's the end of the talk today. Thank you very much for your attention, and I think I'm over in a bit, so sorry for that. But yeah, I'm happy to answer any questions.
So thank you very much, Andy, for this excellent presentation. Let's check the questions here. I have a few ones, to be honest. Let's start here by our finite element analysis. I got curious on that, and when you analyze failure, for instance, I presume you import or you generate a mesh in a finite element software like Abacus or anything else you wanna use. And regarding to failure, how do you analyze that? I mean, failure criteria or any particular boundary conditions that you use or something?
Yeah, so I've tried various ways. Initially, I had a project where we were investigating failure before we made these findings that the interlayer strength was potentially the same as the bulk material. So for those models, we started with the idea we'd need some kind of interfacial layer between the elements of two different filaments, some kind of cohesive elements or something that would allow us to put in a lower strength interface. But then after doing the experimental work and realizing that the actual strength of the material there was bulk strength, we've moved away from that, and basically we can get really good predictions of strength with very basic assumptions of a kind of failure strain. So just whenever the material reaches a certain strain, it will fail. And my students currently writing up, hopefully, one of these papers which is showing that, and showing that really the geometry is absolutely the most important thing there, and actually the FEA is relatively simple.
Oh, cool. That's very interesting. So that's I think this thinking is also part of one of the results we showed when you compared the printed structure with that one like perfectly, let's say perfect, let's say with grooves.
Yeah.
Wasn't it? Okay. Oh, cool. Yeah, that's very, very interesting, because usually we go after like failure criteria, and we try to model all the details in the microstructure to test it and things.
Yeah, and the models I've seen generally don't have the mesh is nowhere near the resolution that would be required to actually accurately represent what stress is happening from the geometry of those grooves. So we tend to have at those grooves, tens of elements just for at the very, very tip of there, and then gradually expand. And this is obviously a really tiny area. So when you go to large 3D models, that's not going to be feasible. But because we're doing relatively simple structures, and actually ours are kind of two-dimensional because they're just continuous in the thickness direction, then we can put in much, much finer meshes. So the stuff I generally see in the literature is more the failure mechanism, or the failure criteria in those are probably representing the geometric defects rather than material defects.
Okay, cool. So yeah, and we usually think that for instance there is a role also of the material adhesion and things like that, but apparently for those cases you studied, so the most important is geometry.
Without doubt, the most important is geometry. The adhesion between materials does exist as an issue, but it is nowhere near, from our vast studies of single filaments, what the influence of geometry is. When you go to different structures, then I don't know for sure how much that will translate, but we have done multi-lines and found the same factors. But for some materials, we have found a non-bulk strength interface. But what we've also found is that is entirely temperature independent. So it's not about intermolecular diffusion and polymer cooling at different rates and stuff. It's something else. We don't know. I don't think we're actually going to have the capability to pursue that research going forwards because my students are finishing. But it was really interesting that even though there was some kind of interface, the fact that it wasn't temperature dependent means it's not the sort of conventional thinking that you'd have for molecular chains diffusing and reorienting as they're cooling and stuff, because then it absolutely would have to be temperature dependent. So there is something weird going on, and my best guess would be that it's either things like local porosity or the material itself having slightly different chemical kind of compositions in the interface region than in other regions, or polymer chain alignment potentially and stuff. But yeah, it's definitely needs some more research. But I think the research that goes there has to measure the bond area before doing anything else.
Oh, cool. And if I get that correctly, also in Voco and also Voco X, I think it's nice to say that the temperature is not taken into account, isn't it?
No, so it's not my ambition when I first came here was to do these single filaments, get a really good understanding of the bond strength, how temperature is affecting it, and then put that information into Voco and make, super Voco. But it was after doing those experiments that I realized there wasn't a need for that at all. So it's quite good that Voco is potentially more useful in its current form, but it was also a bit of a shame that I had these really logical ways to extend Voco to include interfaces really easily. And I wanted to do that, but it's not necessary, it seems.
Oh, cool. Yeah. Well, let me check here the chat. Is it possible to use full control for multiple extrusion print using different materials for each extruder, for example?
Yes, so I've done a couple of tests that are relevant to that. One was printing with 2 different nozzles, 2 different materials, layer by layer, printing both materials in each layer. And that was, very easy to do in full control. I'm not sure if I've documented it, but there is the option to add tool number. So you can say, for this line, print it with tool 1. For this line, print it with tool 2. And then it will just look, whenever tool changes, it goes and looks up what commands are required to implement a tool change in the G code. So it does that automatically. And the other thing that's very similar to that is when our tool changes, we'd often print with, say, one material and then get the microscope and go and take some images at very specific known X, Y, and Z positions, and then potentially get another material and print, and then go and get the microscope again and look at that. So that's, in terms of G code, it doesn't make a difference really whether it's a microscope or a nozzle, except for you don't need to tell it to extrude material, but the actual kind of the tool paths and X, Y, Zs are defined in an identical way, regardless of what the tool is.
Oh, cool. And just another curiosity. Let's say 2 lines of 2 materials side by side, keeping the total thickness like constant, but varying the thicknesses of the walls. Let's say, can you do that?
Yeah, and really interesting things along those lines. So let's say you do want to do 2 materials into alternating materials, and each line wants to be a different width each time. Then actually a really important bit is going to be how you start that line. And if you're printing a wide line versus a narrow line, then you might need some kind of build up of pressure to get the nozzle in a nice steady state situation. So then also designing the line to run into it, or as you print from one line to the next, a bit of printing which is purely sacrificial to allow the nozzle to stabilize at the new width before you start printing that new width. That's the kind of thing that is really important, where you're not just designing the printed part, but all the other stuff as well, which is often sacrificial material, but it allows the printed part to actually be what you want, not the tool path being what you want, because it doesn't matter if you tell it to suddenly change from one width to another. On certain printers, it's not going to change for maybe 10 or 20 centimeters. So you have to make sure you print for 10 or 20 centimeters before you get to the actual region of interest.
Oh, cool. Well, let's check here. Moving on to the next question. People are asking about the materials that you used for your vertical printings. I assume those like truss-like structures, very interesting, like with no overhang and things.
So the truss-like structures, the stents, these were all printed with pure PLA, and this is a happy coincidence that it's PLA, because as I said, my whole PhD was on bioresorbable polymers, and they were PLA because they're a medical polymer. So this structure here is PLA because it's bioresorbable for those medical applications. So it's just perfect, pure, natural PLA which we buy with no additives or anything, so that we can get decent degradation data and stuff when we're looking for medical works. I can't think that we've done this with a different material than PLA, but I don't think it would be a problem, because we've done these types of structures on vastly different printers with different nozzles, and you need slightly different settings for each one, but it's always been achievable. With regards to these, I've seen people printing them with flexible materials, lots of different polymers, with nozzles that are 5 mil in diameter and nozzles that I was using 0.4 mil. So for these, it really isn't material dependent or nozzle size dependent at all, and that's like got evidence for that. With the stents, I don't think it would be, but I haven't tried.
Oh, cool. And yes, I'm also curious about, for instance, it's a question of printing velocity and also material deposition speed, isn't it? Or
for these,
yeah, could you stress a little bit on the parameters that you use to get all those nice structures without support and things?
Yeah, so, and as you can see here, these ones, they've got those little tails on the top, and they were one of the earlier ones. And at this point, it was optimized to the point where they didn't happen anymore because he'd changed, in this case, this speed. And I believe what we had was that the speed gradually reduced as we went up. There was a certain retraction at the top and stuff. So this is only at 2 times speed. We're not printing super slow or anything here. But the most important thing was, I think, for sure, speed. Obviously, how much we're extruding, and this is slightly separate. You can ignore that was post-processing, but actually how much material extruding is clearly important. But we never really focused on temperature and certainly not material optimization. So I think there's quite a few opportunities there to actually optimize that if it was required, but we didn't need to. We were found that it was successful even without doing optimization of those things.
Okay, cool. So next question here. Let me check. When I noticed that you all like you mechanically test many things. Mm-hmm. So when you have a structure or a coupon, let's say, which is not like 100% in fill, how do you deal with such specimens, for instance? Because you probably in your testing machine you're gonna have something to grab it or a claw or.
So with infill testing lattice structures, let's say most of my earlier stuff was for compression tests, which obviously makes it super simple because it just squash it between 2 plates. But with I have run a couple of projects looking at tensile testing of lattice structures, and again, the way we got them to work was thinking in much the same way about increasing the density, increasing the strength of the structure in the bit where it's clamped. So okay. in an odd thing, what we would actually do is often make it narrower here. So the lattice that is say 50% porosity, if we can bring that in so that it's now 100% porosity, that means we can 100% dense, then we can clamp it really tight, and we're not compressing this lattice structure anymore. We're just compressing solid polymer, so we can clamp it with the grips with enough force without collapsing the structure. So it's kind of an inverse, the opposite of a normal dog bone, where we actually make it narrower, but the important thing is it's denser, and we will, in combination, increase the extrusion width and stuff to make it so that it's the cross-sectional area, the contact area between layers is always higher where we're gripping it as well. So it just is, I don't know what our plans are with that, but I definitely know that for when you're doing those kind of tests, you really do need to think carefully about how to transition in such a way that your structure is always getting stronger, and that is not often just making it bigger, because when you make it bigger, you get changes in the lattice. So if you suddenly go from 5 unit cells to 6, you can get a critical change there where you get actually a poor area of contact between those 2 layers at the transition. So it's, if you just take in an ASTM specimen's overall shape and put it in sizing software, then it's not going to be easy to get it to fail consistently in the gauge section.
Oh, cool. That's very interesting and also very important, I think, as well. Let's check here the next one. So about that sinusoidal pattern that you showed, like 2 crossed sinusoidal patterns. For instance, how do you make for like filling things like in between the crossing lines, for instance? Is it?
Do you mean for these types of structures?
The last one, I think, the first one. Yeah.
This one. And repeat what you were saying. How do I do what?
How do you, for instance, you have some patterns going down to up, and then up and down, and then you also have patterns going from left to right.
Yeah.
And I assume you have to skip one scheme like up down, the other layer like left right, and when they overlap, how do you do for filling, the layers of the same orientation, let's say?
So I'm not 100%. I'll answer. Just let me know if my answer isn't what you're expecting. But in terms of designing the toolpath for this, we've been through a few iterations, and initially it was, as we say, we go up, down, up, down, up, down, and then we can end at the top right is a really convenient place to end. I've got it ending here. But actually, if we end at the top right, then what we can do then is come left, right, left, right, left, right, left, right, left, and end at the bottom left. So then after printing the vertical ones and the horizontal ones, we've started and ended at exactly the same point. So now we can move up and print the next layer. The one issue with that is that these lines, the horizontal ones, are kind of colliding and printing through the vertical ones. And you do get some defects there, really microscale defects, where the filament, as you're printing towards a line, it will get a bit wider. And then after the nozzle crosses the line, it takes a little bit of space for the actual extrusion to get to its full width again. So there's this kind of narrowing, and that is a mechanical defect. The one way to avoid that is if you then print in the opposite direction on the next layer, then the defect will be on the other side of the line, and you'll have a bigger buildup on the same side. So you can kind of offset those defects. We've also tried things like moving the nozzle up slightly and down slightly as we're going over a previously printed line. But in actual fact, we've just published a conference proceedings on it. The real simplest and best solution we found was to print all of the vertical ones at one Z height, and then move up by half a layer, and then print all the horizontal ones. So you're only blocking the bottom half of the filament. Then you move up half a layer and print the vertical ones. So again, you're only blocking the bottom half of it. And that means you have the same conditions for the ones that are printed vertically and the ones that are printed horizontally. So you don't get this asymmetry where we were finding the strength in the Y direction was literally 4 times the strength in the XY direction, just because of the sequence in which it was printed. Once we do this half layer offset, we've found it that it becomes sort of isotropic in the Y and X and Y directions. Anyway, we have the same properties.
Oh, cool. So in this way, with those mechanisms, so you can have a nice infill without gaps between layers, for instance.
Yeah, you don't have. Yeah, for sure.
Okay, cool. Let me check here. Next question. How about, Andy, how you said something about composites and challenges for future as well, and free-form design. How do you see these things? I mean, how do you see like full control or another tool applied to optimization for composites and free-form design, for instance?
Yeah, so a lot of the stuff I've talked about today and shown has been with the Excel version of Full Control, which is published as Full Control G-Code Designer. But all the stuff I've been doing over the last year is with this new follow-on version, which we just call Full Control, which is then written in Python. And basically then you have all the power of everything everyone has ever written in Python before at your disposal. So you can do FEA in the design, you could do optimization and AI aspects in the design. So your toolpath design isn't so much defining what X, Y, and Z are, it's defining a method to identify what X, Y, and Z should be. But there's lots of different ways of doing that. With this example, you know, I could design that lattice with a rule that it's definitely going to be 4 filaments printed. This is currently 4 filaments printed, so that I know I can go up, down, up, down, up, down, up, down, and end and start at the same point. But then aside from that, let optimization do whatever it wants in terms of how those 4 filaments are moving. And that might link in with Python modules that are doing finite element. It might link in with other software that's doing things, as long as you've got that communication. So where I'd see it is the design of the toolpath is not just you thinking what X, Y, and Z are, but I thinking what the actual best strategy to identify those coordinates is. And that becomes even more important for 5 and 6 axis, and also for 4 and 5 axis, and also for that's what I was just going to say, for incorporating external data like STL files. So I could take this lattice geometry and wrap it around an STL file, and just, that would be super simple and easy to do, because there are packages out there for Python that do STL processing. So that's where I see the future is really empowering people with many of the simplicities and kind of design methods that full control in Excel encouraged, but with this massive breadth of freedom to do whatever they want in really whatever software they want, because Python can talk to them all really easily, whereas Excel is much more a standalone program with Visual Basic working on its own, and it's not nice for communicating and with other things.
Okay, thanks for your view, Andy. And another question here is, how about aerospace structures? Because in aerospace we often like for instance structures with low infill, you know, with lots of reliefs and stuff. How do you see some do you see applications for those microstructures in aerospace components, or in any other engineering fields that may require like low infill structures or mass savings?
Yeah, so I'll come back to my faithful phone holder example, but a couple of things. Firstly, in terms of optimization, if the current approach for optimization, where you're generating an overall geometry and then figuring the toolpath out for it afterwards, you'll end up with nowhere near comparable properties in your printed part compared to your design part, because you're just not going to get solid polymer where your topological optimization is asking for solid polymer. Whereas with this path, it's really predictive as to what the mechanical properties would be. Even the kind of weaknesses, the bond between the lateral filaments here is highly predictive without a doubt, and the prediction of strength in between the layers here is just super easy, because every layer is basically identical. There's a bit of fluctuation from top to bottom, but without a doubt the Z direction there is really easy to predict. So with this simple toolpath, all the kind of understanding that I was doing about single filament mechanical testing, this is just a series of single filament walls kind of stuck together at various points. So all that really nice predictive capabilities we have from, and really good understanding about how to improve the strength in the Z direction and also in the XY direction, is really translates very simply to this overall geometry. So what you'd end up with is firstly better mechanical properties, because you're actually designing a structure that is optimized for the process in terms of the process capabilities. But secondly, a much better link between what you're trying to optimize, the kind of what you're actually printing, and how you're optimizing it, if that makes sense. So you're not optimizing for an overall geometry that then when you print, you don't get the actual properties you expect. Here, you'll truly be optimizing the final parts properties rather than the properties of the solid model before it's manufactured. So for a critical industry, firstly, the predictive nature of things and the repeatability will be critical. And then secondly, I just think the mechanical properties that you'll be able to get when you truly design a print path and optimize a print path will be far, far better, especially for porous structures, like you say, than what you'd get if you're not fully designing every aspect of the print path.
Okay, that's cool. I also agree. You know, we use lots of assumptions, you know, to model like a microstructure or things, you know, that we can use in a finite element model for predicting properties and things. But when you look at the toolpath, then I also agree that we can also
It's much simpler.
Yeah, it's much simpler and more efficient.
If I took the outline of this and created a CAD model for that and put it into slicing software and then said fill it with whatever 50% infill, it's going to be horrible in many ways, because for starters, if you put a square grid infill or something, it's going to be horizontal here. Now you're going to have diamond shaped pores at this point. Then you're going to be back to square grid pores because of the orientation of that grid. It's not sweeping around with the part. Even if it's triangle or gyroid, it's just going to be different properties here than it is here, than it is here and here. So it's going to be horrible to predict. The contact between the infill and the external bit will vary everywhere and be really impossible to predict as well. So it's just a bad idea, a bad approach in general to actually get a really good part. And if you look at the concrete printing industry, for example, and things that are at that kind of higher level, there's no way they're doing that. They're doing print paths that look like this for the internal sections of walls, because they have to. The material's too difficult to turn on and off. Like polymers, you can turn on and off, so it becomes a kind of normal thing to do, even though it doesn't help. If you can design not to turn material on and off, it's good, in my opinion. But yeah, I think if you look at concrete, you'll see this type of print path, and bringing that towards polymers is necessary if we want the same thing, which is kind of the best performance.
Okay, many thanks. Let me see here our questions. Apparently that's all. And just to let you know, Andy, we have people from Brazil watching us, at least 3 different cities, quite far apart, to be honest, to watching us. Also people from Portugal and UK, of course. Yeah. So thank you very much, Andy. I think we have ended with all questions. I'd like to thank you very much for this seminar today. Thank you all who have been with us today. Thank you for the interaction. Special thanks to Mr. Emerson Batista, who has been working with the IT and all the work on YouTube. And thank you very much, Andy. Again, would you like to say some final words?
Yeah, no, just thank you again for having me. And yeah, if anybody wants to discuss anything further, then just send me an email. I don't think I've put that anywhere on my slides, but if you search for my name and then Loughborough or Additive Manufacturing, I'm sure it will come up. And yeah, I'd be happy to discuss anything further. But yeah, thank you very much for having me.
Yeah, thank you very much. Thank you all. Thank you, and that's the end of the seminar. Thank you very much, and bye-bye.
Great. Bye-bye.